Oh, hello there! My name's Herb, and I'm going to be your guide and shoulder to cry on throughout this biochemical video. We all know that learning all the formulas and metabolic pathways can be quite a pain in the ass. So here I am, to offer you some help along the way. Let's go! Today I'd like to introduce you to glycolysis. This right here is a human cell. To function properly, it needs energy. Unfortunately, taking a nap is not an option for cells. But they are smart, and they came up with a few options of getting that energy, glycolysis being one of them. The word itself tells us what's going to happen. Glyco is referring to a glucose molecule, and lysis means the breakdown of. As the body breaks down glucose, it gains energy. Glucose is a saccharide, or a sugar molecule, and humans receive great amounts of it every day from food. Glucose itself is made up of 6 carbon atoms, and the product of glycolysis are 2 molecules of pyruvate with 3 carbon atoms. Here you can see a rough schematic of the glycolysis pathway. Most of the steps of the process are reversible, except for the ones you see indicated in yellow. Glycolysis is only the first step of the complete glucose disintegration process in the human metabolism. The pyruvate molecules can be further broken down in the Krebs cycle, which we will cover in the next video. Let's go then! First, we'll need glucose. Glucose obviously isn't ready for anything. To activate it, we need to get it phosphorylated, which means attaching a phosphate group to one of the carbon atoms. The phosphate group is a phosphorus atom bound to 4 oxygen atoms. In the cellular environment, the oxygen atoms, bound by a single bond, usually have negative charges. Phosphate can be found roaming free. In that case, we call it inorganic phosphate and write it with an I index. But more likely, it is bound to a bigger molecule such as ATP and its analogs. In an ATP molecule, there are 3 phosphates bound to each other. Because phosphates carry negative charges, which repulse each other, our phosphates really don't like sitting next to each other very much, and are very pleased when 1 or 2 of them can be broken away to produce ATP or AMP. So, as you can see, ATP is very happy to give away phosphate. We can use it to give one to our glucose. To get the phosphate to the right place, it needs a bit of guidance. Here comes one of our enzymes, hexokinase. Hexo means 6, and kinase means it attaches a phosphate to something. So here it will be attaching a phosphate to our 6 carbons containing glucose. What we have here now is glucose with a phosphate attached to the 6th carbon atom. So the product name is glucose 6-phosphate. Very easy. Now that glucose is alive, we can transform it into fructose 6-phosphate, so we can work with it a little better. Here we'll need the help of phosphoglucoisomerase. Isomerase basically means it won't be adding any new atoms, only rearranging the ones we already have. And because fructose also has 6 carbon atoms, that's what we need. Fructose is starting to get a bit tired. After 2 steps fructose, really? So let's boost it with another phosphate. Phosphofructokinase will help us with this one. The end product will be fructose 1,6-phosphate. At this point, fructose is really excited, almost dangerous looking. We'd better diffuse it. Aldolase here is very good with emergencies. Well, now we got ourselves 2 molecules, each with 3 carbon atoms, glyceraldehyde phosphate, or GAP, and dihydroxyacetone phosphate, or DHAP. Unfortunately, only GAP is allowed to continue in glycolysis. But fear not, DHAP, I have just the thing. Isomerase here will convert DHAP to GAP with ease, so we will end up with 2 GAP molecules. From this point forward, every reaction will occur twice, once for each GAP molecule. Please do forgive me, but I will draw it only once. Now we wait for the thieves. GHAP dehydrogenase and her accomplice, NAD+ are on the lookout for hydrogen. But fear not. Inorganic phosphate comes to the rescue, binding to the molecule and creating 1,3-phosphoglycerate, or 1,3-PG. As you might have noticed, I'm using all these abbreviations. That's because I want to ease our minds and not worry them too much about all the long words. Coming to the next step, we need to be cautious. PG kinase, or phosphoglycerate kinase, looks like it has no business with us whatsoever. But don't be fooled, for she is holding the Uno reverse card. Anytime you see that, it is an indication that the enzyme is named after the backwards reaction, or the reaction in the opposite direction. But it catalyzes the forward reaction as well, which in our case is taking away the phosphate group from the first carbon of our 1,3-phosphoglycerate, creating only 3-phosphoglycerate. Here we are closely coming to one of our last enzymes, PG mutase. Mutase means she's a type of isomerase that moves a functional group. In our case, the functional group is a phosphate, and she will move it from the third carbon to the second carbon. Bear with me now, we are getting to the finish line. Analyze here is going to help us create phosphoenol pyruvate. The word enol indicates the existence of the double bond between two carbon atoms when one of them is also bound to a hydroxyl group. See, this setup can exist in another, much more likely conformation, where the double bond would skip to the oxygen atom, creating the keto form. See, every molecule rather exists in the keto form. It's just better. But in our case, there is a phosphate group in the way, and the phosphate group is bound through an oxygen atom and preventing the keto form from happening. Oh yes, I congratulate you. You have successfully made it to the end. This is the last step of glycolysis, pyruvate synthesis. Pyruvate kinase, with a reverse card, will rid us of the last phosphate, and as it is no longer in the way, the molecule will very happily rearrange into the keto form. There she is, pyruvate, causing so much trouble. Pyruvate can continue to many different destinations. For example, in the human body, it can be converted to lactate, or in bacteria, to ethanol. But most importantly, it may go to be further broken down in the Krebs cycle. We will look into that one more closely in the next video. Thank you so much for surviving with me until the end. If you know about someone who would also enjoy this video, please share it. And if you feel extra generous, you may support us on Patreon.